we will discuss about introduction to turbulence. Turbulent flow is one of the very fascinating topics in fluid mechanics, and this is considered to be one of the most challenging problems for which the exact solution has not yet been obtained. People have scratched over the surface to get a statistical picture of what turbulent flow is all about, but the real understanding, physical understanding of turbulence for some simple flows like pipe flows and channel flows there has been reasonably good understanding, but for very complex flows it has not yet come across. So, the first question we will address is what is a turbulent flow? Well, this is a very difficult question to answer, because turbulent flow does not have a strict definition, but it has certain characteristics. So, what we will do is we will try to figure out certain important hallmarks of turbulent flow and bring our analysis in perspective to that. Let us say that we start with something very classical. In 1883, Osborne Reynolds performed a very famous experiment which is known as Reynolds experiment. So, what he did is something which is as simple as this. There is a tube. In this tube a colored dye is injected and the flow rate through a flow controlling valve is progressively increased. So, for very low flow rate you will see the colored dye visible as distinct lines. This shows that fluid is moving in a very ordered and layered fashion. However, if the flow is increased, then this orderly nature of these colored lines is lost, and then the entire thing will appear to be diffused and mixed. Reynolds attributed this to a physical transition from an ordered regular motion to a random chaotic motion in the flow, and that he attributed to some phenomenon known as turbulence. So, question was that if you have a fixed diameter, this transition to turbulence is occurring only for a fixed flow rate for a given viscosity, but if you change the diameter, if you change the fluid property, if you change the flow velocity, you will see that the transition occurs under different conditions. So, Reynolds wanted to analyze these results in terms of the important physical parameters. So, what were the important physical parameters? There is a driving influence, which in this case is inertia force, which is the accelerating component. So, inertia force, this is of the order of mass into acceleration, and there is a resistive force which is viscous force. So, viscous force is viscous stress, where V is the velocity scale and L is the length scale of the problem. So, mu V by L is the shear stress times area is length square. Okay. Mass into acceleration, mass is rho into L cube of the order of, we are just trying to write it in terms of various scales, and A is like for example u du dx. So, u square by L. So, inertia force by viscous force rho L cube u square by L by mu V by L into L square. So, this is, so this u, or you can call it V, whatever, instead of u you can call it V velocity to give the same name to the all the velocities in the expressions. So, this becomes rho V L by mu. So, this later on, to honor the contributions of Reynolds towards understanding this physical phenomenon, was called as Reynolds number. So, this is Reynolds number. Remember that Reynolds number can be interpreted as a non-dimensional length scale or a non-dimensional velocity scale. It may be interpreted in various ways. It is not necessary to interpret it as always inertia force by viscous force. For example, if you have a fully developed flow through a pipe, inertia force is 0 because fluid is not accelerating, but Reynolds number is not 0 because in that case L is the diameter of the pipe, V is the average velocity, rho is the density and mu is the viscosity. This combination does not give 0. So, please do keep in mind that Reynolds number as interpreted by inertia force by viscous force is restrictive. It is restricted only under those conditions where inertia force and viscous forces are competing. Otherwise, it may be interpreted in various ways as dimensionless velocity, dimensionless length, dimensionless time, whatever, but its definition remains this rho V L by mu. That is the correct way of looking into Reynolds number. So, remarkably it was found that in Reynolds experiment, this transition from this ordered to disordered flow was occurring at a Reynolds, at a fixed range of Reynolds number, and that is roughly of the order in the range of 2000. There is a controversy depending on experiments conducted by various people. It may range from 1800 to maybe or 1700 to 2300. So, roughly on an average 2000 we can say. So, that Reynolds number is called as critical Reynolds number for pipe flow. So, critical Reynolds number. Now, here is a very important concept that I want that you please share with your students. Most of the students have a wrong idea that above the critical Reynolds number flow is turbulent. So, the correct interpretation is the other way around, that is below the critical Reynolds number the flow is always laminar irrespective of the level of disturbance. So, what happens when the flow becomes turbulent? So, when there is a disturbance in the flow, the disturbance gets amplified if the flow is turbulent, but the disturbance gets dampened out if the flow is laminar. So, irrespective of the level of disturbance, the flow, the viscous forces are so strong that disturbances dampen out below a critical Reynolds number, but above the critical Reynolds number the disturbances may get amplified or may not get amplified, it depends on the level of disturbance, but below the critical Reynolds number it will always get dampened out no matter how large the disturbances are. So, this is a very important concept. I have seen in my classes that whenever I ask a student what is critical Reynolds number, magically the student says 2000, 2300 like that. So, you have to train your students to understand that critical Reynolds number is not a magic number. It may be whatever, depending on, for a pipe flow it is this, for a channel flow it is something else, for a flow over a flat plate it is something else. So, it is not the number that is important, the concept is important, that below that Reynolds number the flow is always laminar irrespective of the level of disturbance. So, as I told that it is very difficult to have a unified definition of turbulent flow, but turbulent flow has certain characteristics. So, random, disordered, chaotic motion, but we have to understand that any chaotic motion is not turbulent flow. There has to be certain other characteristics. Wide range of length scales and time scales. And a corollary to chaotic motion is that it is hallmarked by extreme sensitivity to initial conditions. And enhanced mixing. This enhanced mixing is very important because that is why turbulent flow is very important for practical engineering applications. Okay. So, we have touched upon random or disordered motion through the Reynolds experiment, but the wide range of length scales and time scales, this we will discuss by referring to a very interesting phenomenon in turbulent flow known as energy cascading. In a turbulent flow, there are many eddies. These eddies are lumps which are physically rotating, lumps of masses which are physically rotating. These are called as eddies. So, you have a large eddy which can be as large as the diameter of the channel, and you can have a small eddy which is of molecular size. So, you have wide range of length scales which have its gradation from the large eddy scale to the smallest eddy scale. So, how these eddies interact? The large eddy extracts kinetic energy from the mean flow. So, there is a mean flow, large eddy extracts kinetic energy from the mean flow. Then what it will do with this? The large eddy will share some of its energy to the smaller eddy, the smaller eddy will transfer the energy to even a smaller eddy, and this is by simply momentum exchange. By simple momentum exchange, the large eddy will transfer some of its energy to the small eddy, small to smaller, smaller and then smallest, and the energy which has been drawn from the mean flow by the large eddy will be dissipated to the smallest eddy, and the smallest eddy being having the length scale very small will have viscous effect much more than inertial effect, and therefore, the smallest eddy will dissipate the entire energy by viscous dissipation. So, large eddy will extract kinetic energy from the mean flow, this energy will be cascaded from large eddy, it will go to smaller and smaller eddy, eventually it will be dissipated by viscous action by the smallest eddy. So, let us say, let us prepare a table like this. So, we have length scale and velocity scale of the large eddy and the small eddy. So, length scale, let us say large eddy length scale is L and large eddy velocity scale is U, just symbolically, and small eddy length scale is eta and small eddy velocity scale is V. So, we are interested to see how these scales are related. This is a fundamental quest in physics which we are interested to address. So, to address that, we can say that the kinetic energy, the rate of extraction of kinetic energy per unit mass per unit time is this one, right. So, this is of the order of, this T is what in a large eddy. So, this is important for large eddy. For large eddy the time scale is the inertial time scale. So, this becomes of the order of U cube by L. And rate of dissipation of, so this let us call this as pi. This is the Eij is the rate of deformation that we have discussed earlier, nu is the kinematic viscosity. So, rate of deformation is velocity gradient. So, this is of the order of nu v square by eta square. The velocity gradient is of the order of v by eta, and rate of dissipation is important for the small eddy, and extraction of kinetic energy is important for the large eddy. Okay. So, to maintain the dynamic condition, whatever is the energy extracted, the same energy is dissipated. So, pi is of the order of epsilon. So, nu v square by eta square is of the order of u cube by L. So, this is one condition. And how do you define the small eddy? See, in the large eddy length scale the Reynolds number is large, that is why inertial effects are important. But when you come to the smallest eddy, with respect to that the viscous force has just started taking over the inertial force. That means viscous and inertia force have become of the same order, that is Reynolds number of the order of 1. So, Reynolds number based on eta is of the order of 1. This is the second condition. This means that so then this epsilon you can write of the order of nu in place of V nu by eta. So, nu by eta square by eta square. So, epsilon is of the order of nu cube by eta to the power 4. So, eta is of the order of nu cube by epsilon to the power 1/4. This smallest eddy length scale, this is called as Kolmogorov length scale. And V is the Kolmogorov velocity scale. Now, although this can be used as a definition of Kolmogorov length scale, you cannot clearly assess what it is because you do not know what is epsilon. You know what is nu, which is the property of the fluid, but you do not know what is epsilon. So, to assess the Kolmogorov length scale, we will utilize this. So, nu V square by eta square is of the order of u cube by L, and in place of V we will write nu by eta. From this. So, eta square, so sorry, let me complete the algebra. Nu cube by eta 4 is of the order of u cube by L. So, eta 4 by L is of the order of nu cube by u cube. So, eta 4 by L 4 is of the order of u cube L cube by nu cube. That means, eta by L is of the order of Reynolds number to the power minus 3 by 4. So, this is the relationship between the smallest eddy length scale and the largest eddy length scale, and this can be expressed as a function of the Reynolds number. So, if the Reynolds number is for example 10,000, you can calculate the ratio of these two by considering this order. So, the order can be because it is Reynolds number to the power minus 3 by 4, this order there can be orders of difference between eta and L, at least 3 orders difference you will get, 3 to 6 orders difference if you get, that means you have a wide range of length scales, because eta and L are not the only length scales, L is the largest, eta is the smallest, in between there are various length scales. So, how do you capture these scales? If you do CFD, what will be your grid resolution? So, all these remain to be outstanding problems. The next aspect of turbulent flow that we will discuss is a very interesting aspect which is called as vortex stretching. To understand vortex stretching, we will discuss about the vorticity dynamics first, which is true for all types of flow. So, vorticity dynamics. So, vorticity is rotationality, right, and because there are eddies in a turbulent flow, rotationality is very important for turbulent flow. So, what we will do is we will first write the Navier-Stokes equation. Assuming that whatever assumptions go behind these are valid. So, we will write, use this vector identity. If you recall, we use this vector identity while deriving the Bernoulli's equation. So, this is a vector identity. So, this is nothing but the vorticity vector omega. So, we write rho now. You know, this pressure gradient is something which creates a lot of headache in terms of assessing what it is. So, one way could be that you eliminate this pressure gradient altogether. The whole idea is that if you have head and if you have headache, best is cut the head and then there will be no headache. So, this pressure gradient creates a lot of headache. So, to nullify this, you take curl of both sides, because curl of gradient of a scalar is a null vector. So, if you take curl of this, interestingly the velocity becomes vorticity, and it does not matter whether the time derivative is there, because curl is spatial derivative, it does not conflict with time derivative. So, you have again curl of grad of a scalar is a null vector. So, you are left with this is null vector and here curl of V will become vorticity. Now, we will use a vector identity for this. So, I will write this vector identity from my notes. It is very difficult to remember this, never encourage your students to remember such long vector identities. So, okay, this is a vector identity. You will get this from any vector calculus book. So, now remember this is curl of, so divergence of curl of a vector, this is 0. For incompressible flow only this is 0, right, 0 for incompressible flow. So, minus of this from here will be and another term which we will bring to the right hand side, this term. So, let us write it here for the time being, minus right. So, we can write right. This is a, there is a Laplacian of omega, right. So, this is a vorticity equation, and we will see interpretation of different terms in this if we look into the physically the phenomenon of vortex stretching in turbulent flow. The large eddy has a large Reynolds number in terms of its length scale. So, it is almost inviscid, that means its angular momentum remains conserved, because it does not have any viscous torque acting on it, because the large Reynolds number. So, for large eddy moment of inertia times angular momentum, that remains conserved. So, that means d dt of I omega for a large eddy it is 0, but for a small eddy this is related to the viscous torque. For a large eddy this is 0, see this is 0 for large eddy. So, I d omega dt okay. So, if viscous torque is 0 in the large eddy, then what the large eddy is doing? The large eddy is giving its kinetic energy to the smaller eddy. So, that means omega is decreasing for large eddy. If omega is decreasing, to maintain angular momentum conserved, this I must increase, that means the length the large eddy gets stretched, so that its moment of inertia increases. So, this phenomenon is called as vortex stretching, that in the large eddy scale because the omega is getting reduced because of transfer of the kinetic energy, the I becomes increased, that means the length scale gets stretched, and that is how it can further interact with the smaller and smaller eddies. So, this phenomenon of vortex stretching you can clearly bring out from the vorticity transport equation. You see this is rho d omega dt, this left hand side, this is the viscous, right. So, you have identified a d omega dt term here which is analogous to this, you have identified a viscous term which is analogous to this. So, this is the so called vortex stretching term which is associated with the change in the total derivative of the moment of inertia of the elements that we are considering. So, this therefore can be attributed to vortex stretching, stretching of vortex elements as they give out their kinetic energy. So, energy cascading and vortex stretching are two very important phenomena that are associated with turbulent flow. So, today we have discussed the basic physics of turbulent flow and some introductory aspects of turbulence. In the next class we will look into the statistical analysis of turbulent flow, because such flows are very complicated, it is very difficult to analytically treat these flows, and therefore one may have to use statistical techniques. So, in the next class we will discuss about the statistical techniques associated with analyzing turbulent flow. Thank you.